Might not even take the full time this week, but I grabbed a couple of resources and I want to talk through particular topic that I think is useful for you to learn about more about, algorithms and when to use something, what's best in a particular scenario. And it all relates to something called complexity theory. You actually don't even need the prior lessons to really learn about complexity theory. So this is probably relevant to you, Ryan, if you don't have a computer science background. But complexity theory deals with the nature of algorithms or sequences of steps and which one is better when and in what scenario to kind of get to an end goal or a solution. So I have, before we get too far in the weeds, I pulled up ChatGPT real quick and asked it to give me some examples because I want to give you a feel of intuition before I talk through. I have an article written on my website and we'll talk through kind of the deeper theory, which I think is pretty interesting and fundamental to everything we know in mathematics and computer science. But we kind of mentioned, I was getting into it in the last prior lessons about basically big O notation and complexity theory, but it's kind of hard to describe when to use a particular sorting algorithm or when to use a particular data structure without describing first complexity theory. And so complexity theory in itself is, comes down, the way we basically notate it is using something called big O notation, which you kind of see over here on the right. There's big O of 1, there's big O of n, big O of log n, and so on. It's not like an equation or anything, it's literally just symbology to represent something. So when we write an algorithm, could be a for loop, could be a really complex algorithm, like a dynamic programming type of thing. And we can characterize this kind of with mathematical symbology in big O notation and kind of know how good we're doing based on the context of the problem. And so the first thing to know is kind of the basics of different, big O's that are common and that you will see. So the first one is big O of constant time. Like, for example, big O of 1, big O of 2, big O of 3, like a specific fixed number. And what that means is that basically it is a constant number of operations to get to the solution no matter what. And so, for example, whether a number or what piece is on a specific square of a chessboard, if I were to write an algorithm for that, it would be constant time because I could go directly to that square and read the piece. And so there's no other operations. I don't have to do all these different sequences. I know where the square is. I look at it. I tell you the piece. So that's constant time of 1. And there could be constant time of 2. Maybe no matter what, it's always 2 operations to get to the end. But the point is that it's constant time. It doesn't scale as the problem scales. The next thing, step up from that. So constant time is the best, obviously. The next one that gets more complex and takes more operations to complete is called, linear time, big O of n, which basically means that, as a problem expands, the number of steps expands linearly, just along a line. So, if it's a very simple problem, it might be 1 step. As the problem gets just a little bit bigger, linearly it scales to 2 steps. And so counting the remaining pieces on a chessboard by or checking every cell in a Sudoku grid is a linear time operation. So I'm trying to think about how counting pieces on a chessboard. So depending on the number of pieces left, you're just going to count up until you've counted the number of pieces. Also, another example of linear time is you have a straight list of information in a sequence, and you just need to find, you need to walk through them and find the highest number. It's ordered or something, but you kind of have to walk through each step or through each piece of memory to get to the final one. That's linear time. So I have like, if I have a list of 10 and I know that the final element is the 10th one, but I have to go in order to get to it, to read it, then all of a sudden I have a linear time algorithm. And if it expands to 1,000,000, then it's 1,000,000 steps. If it expands to 1,000,000,000, it's 1,000,000,000 steps. But the point is it's exactly linear in its scaling of the number of steps to completion. Linear is also great. We love linear in computer science. It makes things pretty easy with modern processors. The next one is logarithmic time. So an example of logarithmic time would be, guessing if a number is higher or lower, or, finding a word in a dictionary because you're like using letters A, then B, then the next letter, and you're kind of zooming in to the answer. So, going high or low. What you'll notice is if you write an algorithm to do this kind of high or low or guess and check game all the way down, you'll end up with a logarithmic time, which means as the problem gets bigger, it expands logarithmically. It doesn't go way up. It's also not quite linear. It's logarithmic, so it's going to continue to approach, asymptotic. Logarithmic is decent. There are certain sorting algorithms that are logarithmic that we tend to bias towards because they're a little bit better from a complexity standpoint. So that's logarithmic. Then you start to get to polynomial. So you're going to kind of get a polynomial ramp up, which is it's a steeper ramp up than logarithmic time. So for example, checking every pair of chess pieces to see if they can capture each other. That's just big O of n squared, because you're basically just, checking, can this one capture anyone? Can the next one capture anyone? Can the next one capture anyone? So you're going to have to loop through the box twice, essentially. So that's called an exponential time problem, or not exponential, that's called a polynomial time problem. And there are various elements of polynomial time problems. They can increase in scale as you go. But the point is that basically big O of n to c, where c is a constant, but it's going to be a polynomial time solution. We also, believe it or not, like polynomial time problems a lot better than the next two, because they tend to be just easier to solve with a computer in terms of the amount of steps it takes. We get really bad after polynomial time, which is when we get to basically all the non-polynomial time algorithms, where it's like exponential or factorial, where exponential would basically be like, c is constant but n is not constant, and all of a sudden, the larger the problem gets, the steps to solve the problem increase exponentially. And so that creates like a massive problem from a computational standpoint. It might be okay when I have a really, really small like Sudoku grid. But now if I have to solve it and it expands all the way out here, it steeply becomes a giant problem. Similarly, chess. If I start from just a particular chess solution and I just want to evaluate the min-max, algorithms of like a branching tree structure, it like exponentially gets bigger, which is a big problem from a solution standpoint. And then factorial is like significantly worse than that, where now you're trying to evaluate every move order in chess. So rather than just like an expanding tree, you have an expanding grid of like, you can think of it like an expanding map of solutions that just keeps expanding. And so, why did I try to write these down was I wanted to just give you intuition for the topic we're about to talk about next. In complexity theory and kind of the deeper pieces of computer science. But these are really the day-to-day tactical things that you'll use. So if you're writing like for loops and they're like triple nested, but you can find a way to do it in linear time or logarithmic time rather than triple nesting for loops, that's a smarter way to approach the algorithm. So that as the amount of things of scope of the problem, grows, the time to completion doesn't get so bad. Does that intuition make sense? Any questions on this before we talk about the next topic? Cool beans. Alrighty, I'm going to switch tabs here. I could send you a link to this later. I wrote this when I was in college, I think back in like 2019, 2020 timeframe. And my master's degree, and it's focused on complexity theory, and we're just going to kind of walk through some of the details here and talk about fundamental problems in computer science. So, like we kind of talked about, complexity theory deals with how complex a problem is to solve, how many time steps it really takes to solve as it scales. And it has kind of profound and consequential, consequences for computer science and mathematics. Obviously, big O notation is something we just talked about. Polynomial times, exponential time, and factorial time, kind of the scaling here. You'll be surprised how fast these things come up when trying to solve algorithms. Everything from projecting pixels on a computer screen to dealing with vectors and, highly nonlinear spaces. Let's see here. Here's an example of big O1. It's literally just an addition step. It's like the plus in C++. If I'm just going to add 1 to it and return x, then that function is literally just a big O of constant time. It's never going to get harder. Here's another constant time algorithm. This is actually technically big O of 3. I think I have a typo on my website, but it's constant time, right? No matter really what x is, doesn't really matter. It's always going to come out to be, constant time algorithm, which is really nice. If we jump down a little bit, big O of n has 1 for loop in it. So if you have 1 for loop of size x, then whatever x is basically your linear time to solve, because you're just going to go through it x number of times. So that's a big O of n. Let's see. Next we have this is also a big O of n. It'll probably surprise you a little bit. That because it's not a nested for loop, it's 2 for loops. Still big O of n. It might be big O of 2 times n, but the point is that or 2 times x. The point is that it's linear. It's not exponential in terms of its growth. Here's another function, and now we get to our first nesting of for loops. So this is the first polynomial time algorithm, where we now have to loop through every element, x squared number of times. Whatever x is, we now have to do it x squared number of times. And so we're now in the polynomial world in terms of how many times the algorithm has to run to reach a completion, right? So on this prior one, and I realize I don't have the perfect tabbing, but this and this are under each for loop respectively. Those for loops each run through, in sequence. So this is linear, and this is polynomial because it's nested. Does that make sense? For these two at least. Give me kind of a thumbs up or something. Sweet. Cool beans. We'll keep moving. So now we get a little bit worse, but it's still polynomial time. But it's triple nested for loop. And so it's going to be big O of n to the third. Really of x to the third, because x is what's determining kind of the scope and scale. And then we, let's see, this is just an illustration of so on and so forth. Like you can keep nesting them, they'll still be polynomial time, but they'll get, worse and worse and worse as you keep nesting them. And I don't think I did any expedition where I showed exponential ones in terms of algorithms. Let me try to think real quick. Is there a way I could communicate exponential? Big O of C, so we need C to grow. So exponential would be like if I passed in x and y, and I looped through x, and then within it, the number of steps that was determined, maybe I had a nested for loop within it that would be y, and then I just kept nesting x and y. I believe that would end up where it would be x to the y, and you'd now end up in this exponential time algorithm. So you can see how quickly just passing in multiple variables to functions with multiple for loops can get you into this world where it starts to become hard for the computer to solve it and take a lot of time. So that's all kind of background tactical theory. What I really want to get to is talk about complexity classes. And this gets very deep into computer science, so welcome to kind of PhD 101. But this diagram down here is a really good illustration of what I want to get to, which is a problem called P equals NP, which you may have heard about before, because sometimes it comes up in everything from philosophy to mathematics. But the P class of problems stands for kind of all the problems that can be solved in polynomial time, which we kind of consider good, like just standard nested for loops or better. NP problems actually stands for something called non-deterministic polynomial time problems. There's kind of a history for why it's not non-polynomial time problems. It's non-deterministic polynomial time problems, which gets to determinism and all this other stuff that I don't want to get into now, but you can probably learn about in the video that I sent you. The reality, though, is that you reach these two classes of problems where you have problems that are easy to solve and problems that are hard to solve. And what we noticed as we kind of went into computer science throughout the 50s and whatnot is that most of the algorithms we faced fell into these two categories. Polynomial time itself was easy to solve, and NP hard problems were really hard to solve. Well, every once in a while, we would kind of find an NP hard problem. We would find a P time solution to what we thought was an NP hard problem. And by recharacterizing it or doing some fancy math to kind of recharacterize the way we would go about finding the solution, we would turn an NP problem into a P problem. And so what ends up happening is people, consistently would find these problems or these creative solutions to turn these problems, NP problems, into P problems. And the question started to emerge, does P actually equal NP? Meaning, for all these really hard problems, are there polynomial time solutions? And we just haven't invented the mathematical framing to solve them in polynomial time. You may ask, Ron, why does any of this matter? It doesn't just matter for algorithms within a computer science context and making like your algorithms efficient and solving problems really fast. And the video that I sent you gets into this, but like problems like protein folding and solutions to cancer are NP hard problems because of the amount of complexity in protein folding. Problems with like non-solvable or non-easy solutions like fluid dynamics fall into like NP hard problem classes. And if you can solve those, you end up being able to solve a whole lot of mysteries that we have within the world today, or things that we just don't have we have approximate solutions for, but not like real solutions for. So there's kind of these two classes of problems, and there's this fundamental question with all these problems: is does P equal NP? I will say that most people don't think P equals NP at this point, but no one's been able to prove it mathematically. And it's actually probably the hardest problem mathematically to prove or disprove one way or another. And I can tell you all kinds of fancy, methodologies that get into like Gödel's completeness theorems and items like that of why or why not we might be able to solve it, but no one really knows is the answer. And so this, along with a few other problems, became a millennial prize problem that came out in the early 2000s, where a particular institute said, we'll pay you $1 million if you find a solution to P equals NP, whether it is or isn't equal. And obviously, no one's ever found a solution. This will probably be the last one to be solved of all the millennial prize problems. And of all the problems, only one has been solved to date over the last 20 years. You get $1 million if you solve it. That was a lot more money back in the 2000s. But it's really a fundamental problem of steps to completion. There are also, we talked about problems that are hard to find a solution for. There's also kind of the counter to the P and NP problem, which is co-NP. And co-NP are basically a subclass of problems that, rather than being easy or hard to find a solution, it actually becomes really easy to exclude non-solutions. And so what you'll notice here is that these classes start to break apart into all these other subclasses of like problems that are, maybe it's really hard to find a solution, but it's really easy to check the solution once it's found, or it's really easy to exclude a non-solution. And there's different framings for all of these problems. And so when we start to look at algorithms, you start to be able to see them in terms of these complexity classes, and which framing and which algorithm to select really depends on the complexity class that it's in of what you're trying to solve. And so I have a bunch of details here in the article, kind of talking about like P problems can be solved at polynomial time, NP cannot be solved at polynomial time. Co-NP problems can be transformed, or I think NP problems can be transformed to co-NP problems for certain classes. There's different types of overlap, and fundamentally we just don't know if all these things are equal or not equal. The other thing I'll say is that there's problems that are harder than NP complete, like solving chess fundamentally, as you get deeper into the far exponential corners. But one item that's worth talking about is this thing called NP complete. Now, we haven't talked a lot about Boolean satisfiability problems or some of the deeper computer science stuff. I have different articles on my website. That's probably not really the intent of these initial lessons, but we can always go into them in the future. But NP problems really come down to something that's called satisfiability theory. And it's kind of like if you look at like an if statement or propositional logic, where it's like, is A greater than B, or is A equal to B, or is A greater than B or less than B? That's basically what's called a propositional logic problem. I just explained it to you in terms of if statements. But the reality is that there's a set of solutions to that. If, like, for example, if the propositional logic ones are the and or classes. So if A and B, or if A or B, where they're true or false, that true or false paradigm, you can basically go through and for A and B assign, A equal true, B equal false, and so on and so forth. And you can build a table that shows you when the expression is true and when the expression is false based on the different pairings of A and B values. That's called a satisfiability problem. And, it's pretty fundamental because it affects like every single control flow in programming of like A and B or B, etc. in the bigger expressions. Well, that satisfiability problem, it turns out that satisfiability problem is almost the definition of NP complete problems, where we are pretty sure that there's no way, or at least we don't think there's a way to translate NP complete problems into polynomial time. No one's found a method. We've never proved it. But if you can transform an NP problem into a satisfiability problem, then you know that it's NP complete and that there's no algorithm that we know of that exists to transform it into P. If you can't transform it into a satisfiability problem, then you might have an opportunity to find a way to transform it into a polynomial time algorithm. I know that was a lot of word speak and a lot of kind of complex and deep theory items, but I felt like getting through big O notation and kind of explain to you complexity classes would be useful as we kind of head forward into algorithms for you guys to kind of know when or when not to use a particular thing, like a data structure or something.